Hello everyone, today we are going to learn a bit more about machine learning by building a naive-based classifier for nominal data from scratch. So we are going to use Python as the programming language and the Pandas library to manipulate data frames. Before we dive into the code, first I want to explain the theory behind the naive-based classifier. For instance, how does the prediction algorithm work, why it is only good for data with independent attributes, etc. So if you are only interested in the code, of course you can jump to the coding part of the video. Naive-based classifiers are a family of probabilistic classifiers based on applying Bayes' theorem, named after Thomas Bayes, which is this Englishman from the 18th century. And this theorem describes the probability of an event to happen based on prior knowledge of conditions that might be related to the event. If you are confused right now, please just stick with me a bit more so I can show you that this is actually way simpler than it looks. To understand the Bayes' theorem and how the naive Bayes classifier works, we need to understand what conditional probabilities are. A conditional probability is the probability of an event A to happen, considering that a related event B has happened or is happening simultaneously. We use this vertical straight line to represent this relationship between A and B, and we read it as the probability of A given B, which is equal to the probability of A intersected with B divided by the probability of B. It's way easier to understand with an example. So let's imagine you have a football field nearby your house and you realize that the weather conditions are somehow related to the probability of having a game in that soccer field or not. So we can calculate the probability of a game happening given that it is a sunny day using the aforementioned formula. The probability of having a game given that it is sunny is the probability of having games in sunny days, that is the probability of the intersection of having a game and having a sunny day, divided by the probability of having a game regardless of the weather conditions. So we have a record here with 10 days and we have the weather conditions. It could be cloudy, rainy or sunny, represented by those emojis. And the row below we have a register if a game happened or not in that day. Then all we need to do is to count how many sunny days we had games, which is 4. And then we divide it by the number of games that we had regardless of the weather conditions, which is 6. So the probability of having a game given that it is sunny is 4 out of 10 divided by 6 out of 10. This is not necessary to know, but I want to show you how to prove the Bayes theorem from this formula of the conditional probabilities that we have just seen. So the probability of A given B is the probability of A intersected with B divided by the probability of B. If we pass the denominator to the other side, multiplying, then we will arrive at this. If we use the same formula to calculate the probability of B given A, just inverting the order of A and B, then if we do the same thing, we pass the denominator multiplying, we will arrive at this. So it's important to know that the probability of A intersected with B is the same thing as the probability of B intersected with A. Because let's think of our previous example. The probability of having a sunny day and having a game is equal to the probability of having a game and having a sunny day. The intersection or the end operation is commutative, so the order doesn't matter, and those two things are one and the same. Now that we know this, we can take this and substitute it there. And this gives us the Bayes theorem. Okay, but what are we using the Bayes theorem for? What is the goal of our classifier? Our objective here is, given the values of a list of attributes, that is conditions, we want to predict the occurrence of a related event, which we will refer to as a class. So basically, we apply the Bayes theorem to calculate what is the probability of this list of attributes having certain values, given that they could belong to a class. And we do it for all the different classes in our data. Since the probability of an attribute to have a certain value is constant for all classes, we can just ignore it. And therefore, the class which maximizes the value of this expression is the most probable class, and the result of our prediction or classification. I know that I am explaining things in a very abstract way right now, but don't worry, I will present you another example very soon. So the naive Bayes classification algorithm is called naive because all attributes are considered independent, that is, they don't influence each other. Since the probability of a sample of our data to belong to a certain class is calculated through multiplication, having two attributes with strong correlation implies that we have two redundant factors in our multiplication, which will give us a Bayes result. One step we could take to avoid this problem is to eliminate one of these attributes to avoid redundancy. So let's just review so far what we have seen, that the naive Bayes classification algorithm depends on this probabilistic model, and this probabilistic model is built through the estimation of the probabilities of each class, and of each class given a certain value of an attribute. And the class, which is the result of our prediction, must have the maximum value of this expression. If you calculate this same expression for all classes and all attributes, the class which has the maximum value is the one that is most probable. Finally, let's see an example. Here we have our formula, just that we can cheat a bit. And we have this table with 14 records or sample. Each sample has 4 attributes and 1 class. Similarly to the example we have seen before, we're trying to predict if there is going to be a game or not. In this case, it's sport. And we will do that considering the weather conditions. Let's say we know the weather conditions. So we want to know if there's going to be a sports practice or not based on these weather conditions. We know that the outlook is sunny, the temperature is cool, the humidity is high, and the wind is strong. First, we need to calculate the absolute probability of each class. In 9 out of 14 records, the class sport has the value yes. So the probability of yes is 9 divided by 14. By the same reasoning, the probability of no is 5 divided by 14. Now for each of the attributes of this sample, whose class we want to predict, we need to calculate the conditional probabilities considering each class. The probability of the outlook to be sunny, given that the class sport has the value yes, is the proportion of records with sunny outlook between the samples classified as yes. So if you consider only the orange rows and you count how many records have a sunny outlook, you will realize it's only 2. So the probability of a sunny outlook, given that there is sports practice, is 2 out of 9. If you count how many white rows have sunny on the attribute outlook, you will get to the number 3. So the probability of a sunny outlook, given that there is no sports practice, is 3 out of 5. Repeat this reasoning for all other attributes to complete the table, and you will arrive at this. Now, all we need to do is to multiply the values on each column to find out the probability of the examined sample to belong to each class. Of course, we are considering only this data set, and we are using this specific method that is the naive Bayes probabilistic method. And as we can see, the higher probability is of the class no, with 2% against 0.5% in the case of the yes class. So this is the result of our prediction. But there is a problem with this method of calculating the probability of a set of attribute values to belong to a class. Suppose that we now want to predict what is the class for this set of attribute values. Proceeding the same way as before, we know that 9 out of 14 records belong to the class yes, and 5 out of 14 belong to the class no. From the 9 records classified as yes, 4 of them have an overcast outlook, but none of the 5 records classified as no have an overcast outlook. So the probability of having an overcast outlook, given that there is no sports practice on that day, is 0. Since we calculate the probability of this sample to belong to a certain class by multiplying all the conditional probabilities related to each attribute, in the second column, the result of this multiplication is 0. And that is a problem because we have only one attribute determining the result of our prediction, which could give us biased results. The solution for this problem is the Laplace smoothing technique, which consists in introducing a smoothing parameter to our calculations, preventing us from having any zeros in one of the factors of our multiplication that could nullify the result. So now all of our factors of the multiplication will be calculated according to this formula. It's not very different from what we had before. In the numerator, we are just adding this parameter alpha to the number of records matching the characteristic we are considering, and in the denominator, we are adding the parameter alpha multiplied by the number of possible values that the considered attribute or class might assume. For instance, since we have 2 classes in the example we are working with, yes and no, we should add to the denominator alpha multiplied by 2. If an attribute has 3 possible values, like outlook, that could be either sunny, overcast, or rainy, we would add to the denominator alpha multiplied by 3. As you can see, it will prevent us from having a 0 as a factor of our product. Let's see now how this works in practice. So we want to predict if there is going to be sports practice today, given that the day has an overcast outlook, the temperature is cool, the humidity is high, and the wind is strong. We are setting our parameter alpha as 1. We have 9 out of 14 records classified as yes. So in our formula, we need to substitute n by 9. Our numerator is n plus alpha, that is 9 plus 1. Our denominator is the total number of records, 14, plus alpha, multiplied by 2, which is the number of possible class values. And the same reasoning applies to the no probability. So the probability of an overcast outlook, given that the class is yes, remember that before it was 4 divided by 9, and now we just need to add alpha to the numerator, so 4 plus 1, and in the denominator we need to add alpha multiplied by the possible number of values that the attribute outlook might assume, that is alpha multiplied by 3, because the outlook can be sunny, overcast, or rainy. Now let's calculate the conditional probability of an overcast outlook, given that the class is no. N is now 0, because none of the records belonging to the class no have an overcast outlook. We add alpha, which is 1, and then we divide this by the total number of records classified as no, plus alpha multiplied by 3, which is the number of possible values assumed by the outlook attribute. And now we don't have a 0 anymore, which is the goal of the Laplace smoothing technique, and we can just follow the same process of multiplying the columns, and that is our result. So notice that in this example, the Laplace smoothing technique didn't change the prediction compared to the previous algorithm. That is, the result of the prediction is still yes. But this could make all the difference in other cases, and notice that the probability of the sample to belong to the null class is no longer 0, which makes sense in real scenarios because there is always some probability of one sample to belong to other classes instead of the one that we are predicting. It could be a very small number, but never 0. Alright, we have covered all the fundamental theoretical concepts, and now let's see how this algorithm works. Let's implement it. Okay, let's do this. So you need to have Python installed and also the Pandas library. If you don't have it, you can Google it, but I'm presupposing you already have Python installed, and you can install the Pandas library just using pip, like pip3 install pandas. I think that should work, or pip install pandas. And this is the data we are working with. It's data about medical exams concerning breast cancer. So either the cancer is benign or it's not good. We have two classes, no recurrence events and recurrence events. This is nominal data, of course. We are creating a classifier for nominal data. And we have information about the patient, the age of the patient, and other things about his condition, like the size of the tumor and other things we don't really need to know about. So let's create a main file, which is where we are going to ask the user for what are the files he wants to import for our program, the training data set, the testing data set, and let's import Pandas, which is the library we use to analyze and manipulate data. And we want to ask the user, what is the file you want us to open to train our model? So let's write train file, and we are asking for an input. What is the name of the file, of the CSV file for the training data set? We will do the same for the test file. Let's just write test file. And we want to know another thing, the class column name, because in this data set the name of the class is class, but it could be anything, and it could be located in any column. It could be the first column or the last column. It could be somewhere in the middle, we don't know, and we want our program to work for different data sets. So let's ask the user that. What is the class column name? Okay, so something in machine learning that is very common is that we need to separate the attribute, the data related to the attributes, and the data related to the class, because we want to make predictions, and the predictions are based on the attribute values. We only have the attribute values and we want to predict the class. So this data should be separated, should be splitted. We already have the training data and the testing data separated, but now we need the X train, which is the data concerning the attributes for the training data set. And we can do that by First we need to open the CSV files. I only have the names, I didn't open them. So we have a train data frame, and we will open using pandas. So pandas.read CSV train file, and we have our test data frame. A data frame is basically a data structure with rows and columns like a table, but also several other attributes that you can check here on the pandas documentation, and methods that you can use to manipulate and analyze the data. So all those methods that make our life much easier. So we can extract all the columns concerning to the attributes from the training data. We take our train data frame and we use the method lock, which allows us to select rows and columns. And we could, for instance, select the first row up to the 10th row and the first column up to the 10th column. But what we want to do here is to select all the rows, and we want all the columns except the column corresponding to the class. We should do the same for xtest. So here xtest, we take that from our test data frame, and we want all the columns except that corresponding to the class. And now we need our iTrain, which is only one column, that column corresponding to the class. So instead of different, we just need an equal here. And ytest. Okay, and for now this is all we need to do. We can test this like printing the first 3 rows or 2 rows, I don't know. Let's print the first 2 rows of the xtrain data frame. And let's print the itest data frame, the first 2 rows too. Let's save. Let's execute this Python 3 main.py. It's asking for the name of the CSV file. And as we can see, it's working as we want. Since it's printing those lines, we know we were able to select correctly just the class column here. And here we have all the attributes except the class. And since that's working, we also managed to read the CSV file correctly. And Pandas is converting the data to a data frame. Okay, so we know that this is working. We don't need this anymore. And let's create our classifier, which is going to be a Python class. And we will later import this class to this file the same way as we are importing the pandas library here. And then we will apply the classifier to this data that we have here. So let's create a file called naive base classifier.py. Let's import pandas. Let's define the class. So we need a constructor. In Python, to define a constructor, you write def, like definition, 2 underlines, init, 2 underlines. Okay, I don't want to do it like this. Let's say the parameters of our constructor is self. Self is like, if you are familiarized with Java, is the same thing as the keyword this. It refers to the object itself that it's being constructed. And I want an optional parameter, which is alpha for the smoothing. It's the smoothing parameter. And I'm declaring it as equals to none, because if you don't define alpha, then it will be none. Otherwise, it will receive any value that you put in the constructor. And if alpha is none, I want to define an instance variable alpha, which is equal to 1. This is the default value for alpha. Else the alpha receives the value passed by the user as an argument here. Okay, this is our constructor, and we need to make a fit method. Every classifier has a fit method, and what it does is to create a model, and the model is basically the algorithm that makes the predictions, the probabilistic model in our case, which allows us to make predictions. And you pass as parameter the training dataset, in this case X and Y, and using the training data you create a model, and then you use this model, you apply the model to the testing data set, and then you can make predictions. Okay, I want to define instance variables storing like xtrain, which is equals to x, and ytrain, which is equal to y. I need the name of the class column, the label of the class column. So getting class column name. I also need all the class possible values, because remember, when we are calculating, we need n vals, and this, in the case of the class, is the number of possible values that the client might assume. In this example is 2, no and yes, but it could be more than 2. So to do that, we can access the y, which is the data frame with the column corresponding to the class, and we get the keys. The keys are the labels of the columns. In this case we have only one key, but I want that as a string, so I'm passing the keys to a list, and then I'm getting the first element. And we need the class values. For that, I can access the column of the class, and then can call the method unique. Unique will give all the unique values in that column, so we have a set of the possible values that the class might assume. And I want to store this information in our object, so let's create instance variables with the same names. I also need the name of the attributes. For that we can also use the keys method, but applying it to the x, because the attributes are stored in x, right? So attributes equal x dot keys, and I want that as a list. Let's create an instance variable to store this in our object. And now to create our probabilistic model, I'm going to use dictionaries to store all the probabilities. So I will have them previously calculated and stored in a dictionary. Later, when I need to make a prediction, I will just access those values. And for that, I need to iterate over all the data. So I'm going to make a join between x and y. So I have the attributes and the class in the same data frame, because then I can iterate through all the data frame to make these calculations that we have seen. And for that, so let's comment here. Joining attributes with class. We are going to store that in a data frame. It's simple as that. And I also need I need to know the number of values per attribute. Because when we are using the Laplace smoothing technique, we need to know n vals, right? So the number of possible values that an attribute might assume. For instance, in Outlook, it's 3, sunny, overcast, or rainy. So I need to know that for all the attributes. And we can do that by an iteration. And I want to store that in a dictionary. So let's declare an instance variable called number of values per attribute. This is how you declare a dictionary. And I already have the names of the attributes. So let's make a for loop. For every attribute in attributes, I want to store it in the dictionary. So then I can easily access just passing the attribute inside the brackets here, and then I will know how many possible values that attribute might assume. And I can get that value by accessing the column corresponding to the attribute and calling the method unique. Sorry, it's not unique. Unique will give us a set of values. What we need is the number of unique values, so n unique. Okay, so now we have the number of values per attribute. I also want to have the conditional probabilities stored in a dictionary. If you don't remember what are the conditional probabilities, they are all those starting from this row. It's the probability of an attribute having a given value, considering that it belongs to a class. So from this row, those are all the conditional probabilities, and those are the absolute probabilities, the probability of a class occurring in our data. Okay, so I have this dictionary declared as an instance variable. I need more things, more information. I need to know the probability, the absolute probability, that is the probability of belonging to a single class. And I will store that in a dictionary too. And I also want to store the number of occurrence of a class. Okay, there is a typo here. So let's create our probabilistic model, which will consist in filling these dictionaries that we created here with the information from the information that we extract from our training data set. And what we are going to do here is basically what we did in here when we were calculating those values using this formula, and we store this information in a table. I'm basically doing the same thing, but I will store the necessary information in a dictionary. So later, when we are making a prediction for a specific sample, a specific case, I can just retrieve the information from the dictionary. I can say I want to know the conditional probability of having an overcast outlook given that the class is yes, and the dictionary will have that information already calculated for us. So just so I don't have to write like things like this, every time I want to use this value, I will declare a variable to simplify our writing. So let's call it number of attributes per val. And I also need alpha. And first we need to calculate the absolute probability of a class. So let's iterate through all class values. Then I can store the number of occurrences of a class in this dictionary for this specific class value. I can retrieve that information from my data frame. The column corresponding to the class, I use the method value counts to count how many times this specific class value exists in our dataset. Now that we have the number of class occurrences, we can calculate the probability of a class to occur, which is the total number of class occurrences plus alpha divided by the total number of samples plus alpha multiplied by the number of values that the class might assume. And so we need the number of class occurrences for this specific class value. We add alpha. This is our numerator, and our denominator is the total number of samples. We can use the length method here to get the length of the data frame. And we need to add alpha multiplied by the number of possible class values, right? So later you can read this with more attention, but what is written here is basically this formula for the class probabilities. Okay, now that we have the absolute probability of each class, we want to calculate the conditional probabilities, and for that we need to iterate through the whole data frame, because we want to know how many samples have a specific value for a specific attribute given a certain class. So we want a data frame just of this specific class value here that we are considering right now. I can do that selecting the data frame only those rows that have this specific class value. Okay, and now we can iterate the attributes, and we also need to iterate all the attribute values. Here I'm accessing the column corresponding to this attribute. I'm getting all unique values and I'm converting that to a list. So every possible value that this attribute might assume, we are going to calculate how many times this specific value appears in this data frame here, which this data frame includes only those samples that belong to the class we are looking into right now. So our n, that is our n here, is equal to the length of df class, and we want to select those samples with this specific value for the attribute. And now that we have n, we can calculate the conditional probability. And we are going to store it in the dictionary using a tuple. The tuple contains the class value, it contains the label of the attribute, and the attribute value. So we can later easily access the conditional probability we want, just specifying what is the class value, what is the attribute we are considering, and what is the value that this attribute is assuming. So this will make our predictions easier. And that is equal to n plus alpha, right? N is the number of samples from that specific class whose attribute has this certain value here, and we divide that by the total number of samples with the specific class. So we want the length of df class, and we need to add alpha multiplied by the number of attributes per value, and we pass the attribute we are considering here. So that is all for our fit method. We are using dictionaries to store all the information we need, and later we will access this information in our predict method. So now we are moving to the prediction method of our classifier. Okay, so let's write our predict method. And this predict method receives as an argument the x data frame. This x corresponds to the testing data, because we have this data that we want to predict, and it cannot be the same as the training data. So we want, based on all the values of the attributes in this data frame, we want to return a list of predictions. What are the classes, the most probable classes for those rows with lists of values? And so we want to return a list of predictions. Let's create a list. And let's iterate through all the rows in the X data frame. We will need to create an auxiliary method that makes a prediction for each row. So this predict method, it's for a whole data frame, and it's returning a list of predictions. We also need a predict method for a single row, and I will call it like underline predict. There are two ins here. And we need to pass the row that we are considering here in the iteration. We need all the values of this row, and we need it as a flattened list because it's easier to work with. Then we will append current prediction to the list of predictions. And after we do that for every row, we can return list of predictions. Now let's write the other predict method that evaluates a single row. And to make the prediction, we need to access our probabilistic model, right? All the information we have stored in our classifier. We need, for instance, the class values. We need to have all the labels of our attributes. We need our dictionary of conditional probabilities. We need the number of values per attribute. And we also need alpha. Since the most probable class is the one with the higher probability, and I am going to iterate to this row, and I will calculate first the probability of the row to belong to the class A and then later to the class B. The one who has a higher probability will be the predicted class. It could be more than two classes, of course, but I need a variable to store the highest probability found up to that moment. I will update P if I find a class with a higher probability. And in the end, the class which gives us a higher value of P will be the predicted class. And I also need to have a variable to store the label of the predicted class. We could leave it empty like this, but for sake of clarity, I want to write undefined, but this will be overwritten later, of course. So we need to iterate all the class possible values. And let's get the absolute probability of a class. So I just need to call P class and pass the class value here. That's the advantage of using dictionaries. I can easily access the values I need using square brackets like this. And let's iterate for all the attributes of this row. I forgot this again. Okay. So there is one thing we need to consider, is that the case that we have a sample in our testing data that we haven't seen before. So our model doesn't have the probabilities already calculated for that specific value, that specific. It's like that zero case when you had an attribute like Outlook and you have overcast given that is sunny, and you don't have that anywhere in your training data. So if we try to search in our dictionary for that specific value for a given attribute considering a given class, it won't find anything because it was not in our training data, and it would cause a key error, a key exception, because you are looking in your dictionary for something that doesn't exist. So we need to check if the attribute with the value we are considering here, we need to check if it exists in our dictionary, and we can do that by passing a tuple. We have our class value, the label of the attribute we are considering, and the value that this attribute has. And we are checking if this tuple exists in our dictionary. If it does, then we just need to multiply what we had before by the conditional probabilities of this tuple here, because we know that it exists, so it's already stored in our dictionary. But if it doesn't exist, then we will use the Laplace technique to avoid a zero as a factor of our multiplication. First, let's get our n here. We need it as a float, so here we are checking how many different values this attribute might have. This is our n. Sorry, this is not our n, this is any vowels. So it's any vowels. Okay. And then we will update p class. And we are applying this formula again. So since n here is 0, we don't have any sample with this corresponding value, we need just to add alpha divided by the number of class occurrences of this specific class plus n vowels multiplied by alpha. Okay, that is all we need to do in this iteration. So after iterating all the attributes for a given class, we want to check if this probability is the highest so far. If it is, we need to update predicted class with the given label, and we need to update p with the current value of p class. It's our current maximum. Okay, and out of these four, we just return our predicted class. All right, this is our predict method for the row. And we can already test it to see if it works. There is some error here. Let's see what it is. Oh, I need to put this here. Okay. Okay, now that we have implemented our prediction methods, there's one thing left that we need to do is to implement our accuracy score method, and it takes an X data frame and the Y data frame. In this case is the testing data. Let's convert the Y data frame to a list. And let's make a prediction. And now we are just going to compare the results of our prediction with the Y list. For every correct prediction, we are going to increment a variable called correct predictions. We initialize it at 0, of course. This could be iList or the prediction list, doesn't matter. So if the value predicted is, if the real class value is equal to the predicted one, then correct predictions plus equal 1. And then this is all we need to do. We just return correct predictions divided by the length of the data frame. So the number of correct predictions divided by the total number of samples. That's our accuracy score. Now that our classifier is ready, we can import it to our main file and we can test it. So we can do that like this. And here I want to create a new classifier, so let's say nb equals to nb, which is our file, and inside of our file we have a constructor which receives as a parameter alpha. Let's set alpha as 0.6. Then we need to use the fit method with our training data. And then we can make a prediction. Let's just test something that it will be interesting. Let's take from our test data, we can take a row like this, is a no recurrence events row. We have here this list of values. And what I want to do is to call that method for a specific row. So I want to print this, let's say nb underline predict, and it receives a list of values, and I'm passing this list here. Oh, this should be, the all should be strings, I think. Let's see if this works. Okay, let's save our file. Let's close this for now. Let's execute it. It's breast cancer train.csv, breast cancer test.csv class. And as you can see, it's predicting as no recurrence events this list of values, and this is exactly the right class for this sample. So this prediction is working, but we should test for our test data. So let's comment this for now. And we want to know, actually we want to know the accuracy score, right? So let's use this function right here, nb.accuracy score, and we should pass the x and y of our training data, right? Because the model, the testing data. The model is trained with this and we want to test this. So let's pass x test and y test, and let's print the accuracy score. So remember, I'm passing the CSV files here. and this will give us the accuracy for all the rows of our test file, if how many percent it was predicted correctly. Let's execute this. So breast cancer train.csv, breast cancer test.csv class, and we got an accuracy of 85%. It's a good percentage, but of course it could be better. One reason that this is such a low percentage, like it's less than 90%, it's because probably some of these attributes, they are correlated. Those are not independent attributes. And one thing you can do is to treat your data to eliminate redundant attributes, and that way you could get a higher accuracy, but it's a good accuracy in general for a classifier that we built from scratch. We can also use more data to create our model. If our model has access to more data, probably it will make better predictions. So I could, for instance, try to copy all these samples in our train2 file. I could join the two files and see if it gives us a better prediction. Let's do this. So I want to copy all of this. Let's go to our first training data. Let's paste it, and now we have a lot of more data for training our model. And let's execute it again. So breast cancer train.csv, breast cancer test.csv class. And we got the same accuracy, so the amount of data really didn't change the accuracy of our predictions. So that's it for now. It's a long enough video. I hope you could learn something with me. I will make all this code and other resources I used here available for you in the description. Thank you so much. If you liked this content, please subscribe and give me your like so the algorithm can favor me. Goodbye.